morning to everyone. We'll start today's VPH Summer School 4-day with the lecture of Dr. Irene Vignon-Clementel. Thank you very much for joining us, Irene. Irene, she is a research director, directrice de recherche at INRIA in Paris. She is leading the real research group that is focused on mathematical modeling and numerical simulation of biological flows. And just talking about her career, she studied engineering at École Centrale, and then she did a master in Cambridge before moving to Stanford to do a PhD under the supervision of Charles Taylor, that is one of the pioneers on cardiovascular modeling and flow modeling. And in fact, Irene's PhD was on this topic, on already starting to couple multiscale and multi-domain models of flow simulation, being one of the big works on this field that really had an impact on the whole field. And after the PhD, well, more recently in 2016, she got her habilitation de recherche. Her main interest in research is quite wide in terms of application, but quite focused on everything related to flow modeling and a lot of different aspects, from data assimilation, from imaging or patient-specific data, to a couple multi-scale models. And in terms of applications, she's been working a lot on cardiovascular, but lately exploring other avenues like in airway applications or oncology applications. I mean, her CV is outstanding in terms of publications and citations, really good. And also we can see it, I mean, it's not like everyone can get an ERC consolidator grant. So this really demonstrates the high scientific quality of Irene's work. I mean, I haven't really had a lot of interaction with Irene, unfortunately for me, during these years. But what I remember, it was that in FIMH 19 in Bordeaux, one PhD that I was co-supervising with Maxime Charensa in France, and it was on coupling cardiovascular models with brain data, and there was a lot of lung models around. And the paper and the talk, there was a lot of numbers, a lot of models, etc. And probably almost no one realized what Jaume was explaining there. But then Irene, after the talk or discussing with Jaume, the PhD student, she told him, look, maybe you should look in these values of these parameters on the RV. And we were like, oh my God, what is this? And then we needed to come back and review. And obviously Irene was completely right. There was a mistake in the model that we didn't realize. And Irene just in 2 seconds realized this in all the numbers, etc. So really, I think it's a very good example of, if you have doubts about cardiovascular models, lung models, etc., I think Irene is one of the best people to ask for it. So Irene, thank you very much again for being with us, and the floor is, or the screens are yours.
Thank you, Oscar, for this very nice introduction. I didn't realize about that last example. But yeah, I think it's really important to be connected in research, like to be a connected network. And I think this school is a good example of this. Alphonse Hoekstra also yesterday evening talked about that. And so let me share today indeed about multiscale computational hemodynamics to explore surgical treatments. So don't hesitate if you have questions, even during the talk. I think it's fine. Can be more lively, especially because I don't see anybody and I I have to admit, I like to engage seeing people. So why do we do this? I think I'm taking this quote from the new president, the President Tessier Lavigne of Stanford when he became a new president a few years ago. I think my first motivation about this kind of research is to foster education, so education of young mind and doing research and using creativity for the benefit of humanity. I mean, this interface with the application is for me really important. So why do we do this kind of modeling? First, we do multi-level analysis of flow and transport. And we do it because it has a tight coupling with other phenomena. So, and in all the examples I'm going to show, it's always joint work between our group and clinicians or experimentalists and or other bioengineering groups. So for example, in congenital heart disease, so in disease for children that are born with malfunctioning hearts or like vessels, how they are, here we used flow modeling, multiscale flow modeling to explore when there are very tight stenosis in the airways and when the flow is very uneven. So not much flow is going to this part of the lung from a blood point of view. And you see that it's less grown than on the other side. So here, the question of the clinicians was, shall they intervene first on that side to make it grow first and then on the other side? Or would it be better to do both at the same time? And so with this kind of modeling, we could try to shed light on this aspect. And here, flow is tightly coupled to growth. So to further growth for the child of, for example, the lung. So it's really important to take this coupling into account. Then we also use this kind of analysis to understand how congenital heart disease emerges. So this is joint work with Jonathan Butcher in Cornell, where this joint was with Stanford University. And here they did experiments on chick embryos. These are the arches of the embryo, of the chick embryo, and they did some laser ablation to change the flow. And with a multi-scale CFD approach, we could try to understand how the change of flow was coupled to a change of growth here too, that can lead to congenital heart disease. In another class of problems, we can use CFD to understand the link between the flow in a conduit. So here also pulmonary arteries. This is right out of the heart for tetralogy of Fallopian where they don't have a functioning valve anymore. So we are trying here to understand the link between the flow without the valve or with a new device and that device. So here the question was from a cardiologist, a pediatric cardiologist that had in mind a new device. And so he wanted to test, what that device that had two parts, a reducer and a valve inside, had, what effect it had, and what each part, what the effect of each part was on the flow. Then in respiratory flow, so I spent a few years on that subject because an American student contacted me. She had experiments and she wanted to better understand the results of her experiments between healthy versus emphysema rat. So here tissue structures, and also she had done some experiments on particle deposition in the different regions of the lung to better understand the relationship between disease in the tissue and particle deposition. So for this, we used a multiscale CFD approach to tackle out this phenomena and to better understand how, the coupling between the flow alteration and the transport of particles. And later on, we had another PhD student that was working on that field, and we coupled this kind of modeling with machine learning to be able to localize more easily where constrictions are in the pulmonary tree in the asthma context. And then finally, so in cancer, there is a tight coupling between the multicellular growth. So here we are more at the micrometer scale, 100 micrometer scale, whereas before we were at the macro scale. And in order to understand this link between cells and blood flow, we wanted to parameterize our models from non-invasive microscopic images, so that such as diffusion weighted imaging in MR, where you can see a tumor here, for example. And we realized that a missing link was the one between macroscopic non-invasive imaging and what's happening at the histological scale, where you can slice tissue and stain for example, cancer cell versus non-cancer cells. So we did some work on that too to understand this relationship. Something that I think you should keep in mind as well as a student, and maybe wondering how these kind of simulations are also used more in the industry, is the fact that nowadays the environment is very favorable to such simulations. In fact, now the FDA, so Food and Drug Administration in the US, is really pushing for such simulations to be used to have an approval of a device. So I really believe that this kind of simulation is going to be more and more used, both for research, but also in the context of device or technology approval. So this is raising the question of benchmarking, and also to know which fluid code to use, for example. So we did a little bit of work on that because clinicians were wondering what code shall we use? And so I would argue that for a lot of cases, it doesn't really matter if you use an academic code or a commercial code, but what really matters is to do it well, to understand what you're doing at every level in the chain, from clinical data to results analysis. So now I'm going to spend a few slides on the methods part, namely on the multi-level mathematical models and how do we perform patient-specific simulations. Especially because we need to keep in mind that we have about 100,000 kilometers of vessels inside our body. So we cannot simulate flow in every one of them. Hence this multi-level strategy and the coupling of different types of models to take into account the different parts of the simulation. So what we start with fundamentally are the Navier-Stokes equations, which are 3D equations of conservation of momentum and conservation of mass, where you have inertial forces, pressure forces, and viscous forces due to the blood being a viscous fluid. And you can couple this to the wall dynamics, so or considering the wall of the vessels to be rigid. Now, if you integrate over a cross-section area of a vessel this equation, you can arrive to so-called 1D equations. So you only have the dimension along the vessel axis now. But it has the same physics, conservation of momentum, conservation of mass, and this is for the wall law relating the pressure and the cross-section area of the tube. And then if you further integrate over space, so over a chunk of vessel, for example, you arrive to so-called 0D models or like lump parameter models, which are essentially ordinary differential equations, which again have the same physics. So this first equation is for the resistance. So this is for the viscous part of the forces. And then the second equation is for the inertia. And the third equation is the capacitance due to the elasticity of the vessel wall. So here we arrive at an analogy with the electricity, in fact, where pressure is like voltage and flow rate is like current. So if you know about electricity with resistances, inductances, and capacitances, you can use this analogy for blood flow as well. And you can also couple these biophysical mathematical models with machine learning, and I will give an example today about this. So how do you select if you use 3D models, 1D or 0D? So of course, it depends on the clinical application or the questions you are trying to address. This question has to be designed with clinicians, for example. So if the phenomena really has a 3D component due, for example, to complex geometry, or if you want to really know the detail of the flow field so that transport is accurately captured between the different parts, or if you want to look at phenomena of different regions here of the heart muscle, then in these cases you need a 3D model. But in other cases, you're rather interested in waveform phenomena. So what's happening during one cardiac cycle. So here in the flow rate, when there is, for example, a surgery, such as removal of a part of the liver, partial hepatectomy. And here we wanted to understand, for example, this change of flow waveform and what's happening during systole. Due to the surgery. And for this, we use 1D wave propagation model, where we could model what's happening from the heart down to the organ of interest. And with this kind of model, we could, for example, understand that this change of flow waveform was related to a change of architecture due to the surgery. And then finally, in some instances, such as innovative surgery, where maybe I will present that at the end of my talk, we really need to take into account what's happening due to a surgery locally, but also the interaction with the rest of the circulation. And so for this, to take into account the whole circulation, we can use these Drd models where the heart each chamber of the heart can be modeled with a varying elastance. And then each valve between the different chambers of the heart and between the heart and the main vessels can be modeled with, for example, a diode and sometimes more complex components. And then every organ or part of the circulation can be modeled by these electric components of resistances, capacitances. So with this, you can also model what's happening at the microcirculation level because it's cheap enough to compute it in many vessels. And then you can also study transport in it, and we've done some recent work on that. So as I mentioned before, so we can either use 3D, 1D, or 0D model. But if we use 3D model, for example, in an aortic arch after repair here in congenital heart disease, after a stent was put, we cannot, we have to specify boundary condition at the inlets, so here coming from the heart, and also at the outlets of the vessels going to the upper body or the lower part of the body, because how much flow is going in these different branches depend on the flow demand of what's of the many vessels that are downstream of these different branches. So to take that into account, we couple 3D models with, for example, simple 0D models, or we can also couple it with like a whole 0D model of the entire circulation, and we can do the same for 1D equations. Hence the terminology multiscale cardiovascular model, but then to make it patient-specific, one needs to define the geometry, but also one needs to define what these parameters R and C and all these parameters in the 0D model are. So to do that, we try to take into account as many measurements as we have access to. So besides CT or MRI, for example, to reconstruct the geometry, we use pressure measurements from catheterization, velocity measurements for Doppler ultrasound over, for example, here, several cardiac cycle, where you can relate it to the flow rate, if you know the flow profile, or PCMRI flow rate. So this is the flow rate over one cardiac cycle. And then depending on the acquisition, you can trust either mean values or minimum maximum values, or you have access to that only sometimes, or the full time varying curve. And this allows you to do this kind of patient-specific blood flow simulation. So to estimate these parameters, there are several strategies that can be put in place. So here, for example, this is the geometry where we had access to the flow coming in the geometry, and only the pressure difference between the inlet, let's say, and the right side, the left side of the heart, so the very downstream part of the system. So for example, you can, so to estimate all these parameters at the outlet, you can first estimate the global resistance of the first system, of the entire system based on these measurements, and then run a first 3D simulation and compare the 3D resistance, that is the resistance of the 3D part with this equivalent resistance. And if the 3D part has a negligible resistance compared to the overall resistance, you can then tune the 0D parameters without really the 3D part. If not, then you need to take into account the 3D part in the process of the tuning. And then there are different ways to do that, depending on which type of data are available. So a book chapter is going to get out soon on that, because I regularly get questions on how do I do this for my own problem. But the main point is that strategies should be devised according to the available measurements. So their implementation and computational complexity need to be coherent with the amount of information you have. So for a purely 0D model, or for 0D models where the 3D part is negligible, you have one type of strategy. But if you need to take into account 3D models, then you can, for example, have loosely coupled 3D and 0D models where only a few 3D 0D simulations are required. This is quite cheap, and it's okay when the 3D part is not too complex. So for example, you start with the first simulation, then you can estimate the distal parameters. So here, if you have time varying coefficients, time varying measurements, you can use uncertain Kalman filter approach, for example, to estimate these orange coefficients. The black one, you estimate them from your 3D simulation. And then you take these orange distal parameter that you just found, and you run another 3D 0D simulation, and then you do a few iterations like that. And in a number of cases, it's completely enough to reach convergence. Now, in some cases where the 3D part is really with very complex flow, you might need to do this parameter identification with the 3D part, and this is more computationally involved. Okay, so now I've covered some of the methods part, and I'm going to now show you 3 different examples of how simulations can be used to first answer what if question. And this is really a strength of numerical modeling, or what you can do on the computer here, that you cannot necessarily test with experiments, or of course on a given patient, where on a patient you choose to do one type of surgery only. You cannot test different ways. So in this first example, so here we are at the first stage of surgery of a congenital heart disease case, where contrarily to normal, the left ventricle is completely atrophied. So in these cases, surgeon used the right ventricle as the main pump for the whole body. So these kids need very heavy surgeries, 3 surgeries when they are children from newborn age to about 5 to 8 year old. And these are very heavy surgeries. So we tried in an international consortium with the Leduc grant to construct some multiscale modeling of these different types of surgeries, to better understand these surgeries, and also to compare different types of surgeries. So Politecnico di Milano was involved, the group of Alice in Marsden in the US was involved, and there were like 3 clinical sites in London and in the US. So in this part of the work, so we used a 0D model where we had, so the heart part and the lung, the upper body and the lower body. So there are many components. And what we did is that we had access to a number of measurements. And so in red, actually, these are the pressure and flow measurements that we use to tune the parameters. And in green, we use these these measurements to validate the model. So here I'm showing some of the results after tuning. For this patient that was 3 months old, and it was so before the second stage of the surgery. So here I'm showing over two cardiac cycles, for example, the volume of the common atrium, the volume of the common ventricle over two cardiac cycles, what's happening in the valve, etc. And here in red are the measurements that we use to tune the model. So you see that some measurements are very well reproduced. And in particular, the choice of, I mean, we made a modification in the valve model that allowed us to have a valve dynamic that is better compared, that is better captured, sorry, compared to a pure dial-like behavior. And actually, so our model reproduced quite well the Doppler velocities in that location with this kind of double peak like this. Also, we could put in the model, we used in the model data that are taken at different heart rates. So we had to change a bit the methodology of data simulation to be able to infer parameters based on data taken at different heart rates. It also worked in another patient that this time had on top of this congenital heart disease, a valve regurgitation. So you can see that during the cardiac cycle, flow is negative at some point. And for this is the measurements that were used to tune the parameters. You can see that they're quite well represented, especially given that here, for example, the pressure in the flow in the inferior vena cava was really switching from a lot of positive flow to a lot of negative flow during the cardiac cycle. So it's a very challenging case. And here in green, these are validation curves. Here the model is validated. And also what we found is that the model results were consistent with ECG measurements that showed that there was overlap between different phenomena. The model was further validated regarding for both of these patients using the 4-chamber echocardiography and, as I showed before, the valvular Doppler flow and also wall volume from MRI. So overall, we were quite happy with this patient-specific part of the modeling. And we use this as baseline to understand or to better understand the relationship between what the second stage of the surgery is going to do and valve leakage. So, because the literature was all over the place regarding this topic, some papers said one should treat the valve regurgitation before the second surgery. Some papers claim that it's not needed. And I'm going to explain why we have this literature contradicting information. So here I'm plotting the PV loop, so pressure versus volume over a cardiac cycle. When there is no valve regurgitation, it goes like this. And then when we increase valve regurgitation, you see how the ventricle is more and more loaded. So it has to deal with more volume. And also the maximum pressures is lowered, meaning the pressure that will perfuse all the organs is decreasing, which is bad. So this is what regurgitation is doing. On the other hand, the second stage of the surgery is actually unloading the ventricle, so reducing the volume it has to push out, and increasing this perfusion pressure. Hence the discussion in the literature, because these are opposite, the surgery and the viral regurgitation have opposite effects. So the question is, what's happening when we have both? And what's happening when you have different regurgitation percentage? So also, when is it better to repair it, given that every repair has a morbidity and a mortality risk? And what we found is that in any case, in fact, the second surgery is not enough to counterbalance regurgitation. So indeed, the surgery is unloading the ventricle, even with a quite large regurgitation fraction. But in this case, by not much, not enough to really compensate the regurgitation problem. And also the perfusion pressure is indeed increasing, but not much. So overall, the regurgitation fraction after is always more than before. And by discussing with the clinicians, what we concluded was that for low regurgitation, probably it was okay to wait for the second stage of the surgery to have the repair. But for high regurgitation, it was probably better to do it before the surgery and to not wait that the ventricle is more and more damaged. We also studied different types of regurgitation, but not much difference was found between the two. And we also looked at the atrium. So the atrium PV loop has, in fact, two parts, an A loop and a V loop. And we could reproduce actually this increase of the V loop that is reported in the literature when there is an increase of regurgitation due to a change in the model that takes into account viscoelastic effect. What we found interestingly is that for the atrium, the V loop is actually not improved by the surgery, or not much, especially with higher regurgitation. So not only the ventricle is suffering, but also the atrium is suffering. And if we look at the force with the stretch of the sarcomere length, so the fibers of the atrium that is responsible for its contraction, what we saw is that so for the ventricle, it was fine. The surgery was reducing, was putting the ventricle in a better zone. But for the atrium, it really stayed in the not very efficient zone. So this is the not very efficient zone because you have more force, but you are stretching more your fibers, but not generating more force, contrarily to here. So the atrium is really suffering in this context. And this is something that is not easy to measure. So that's the kind of output also that the model can provide. Okay, so that was a good example of how we can use simulations to pose a what-if question. So what if I repair the valve at the same time of the surgery? What if I make the valve regurgitation worsen? What if I repair what if I repair the valve when the regurgitation is really high? But now simulations can also be used to study growth phenomena. And this is where we use a combination of simulation and machine learning. Here with a completely different type of disease. It's acquired aortic disease. So this means it's disease that develops over the years. So the context is abdominal aortic aneurysm. So it's an enlargement, a localized expansion of the aortic wall in the aorta, in the descending part. It's usually asymptomatic, but if it ruptures, there is a quite high mortality. And the prevalence in the population is quite high. The incidence is lower for women than for men, but it has a higher risk of rupture. And it's related to a number of comorbidities. You can treat aneurysms by putting a graft, a stented graft inside, or by open surgery. But ideally, this is only performed for high-risk patients. The local criteria right now to perform surgery is only the maximum diameter, but clinicians know that it's not enough of a criteria to really take, let's say, good decisions. But for now, that's the main criteria clinically. What they really need, in fact, is a tool that can predict aneurysm progression, because some aneurysms actually don't grow much at all over years, and patients, keep them over years without any problem. But some other patients have a huge growth of the aneurysm, and this is present higher risks. So the process of aneurysm development is not fully understood, but the current theory is that there is some kind of a deformation that occurs due to mechanical adaptations, a shift of elastin to collagen ratio in the wall of the aorta, and these have an effect on the flow field inside the aneurysm. It changes the topology of transport of the wall shear stress, and so it has an effect on the thrombus growth. So thrombus is forming inside the blood vessel. This is what we can distinguish here between the lumen of the vessel, which is red, and the aneurysm sac, which is in gray. So the difference is this thrombus that forms. So this thrombus forms due to platelet activation in high shear zones, and deposition in stagnation zone. There is a increased platelet adhesion on the thrombus and in the lower shear stress zones. So there is a tight coupling between the flow and this growth phenomena, which can then further promote wall degradation, and then you have some kind of vicious circle. But as you can see, for some patients, first the growth can be very, very, very silent in a way, not much growth over years. And for others, it can be with a very different shape and with a much larger growth over time. So the second question that we wanted to address was, can we identify a correlation between flow alteration and aneurysm growth? So the methods are the following. We started from 138 scans. So for 32 patients, we had access to 3 consecutive scans and also 9 control scans. From these scans, segmentation of the lumen and of the ILT was performed. And then we run pulsatile 3D 0D simulations. Here with rigid wall, non-Newtonian fluids, we needed to have some stabilization of this is more like technical, but of the flow field at the outlets. So the student that did that had done some preliminary validation of the flow he was obtaining with MR at a different location. But in this work, what we did based on this CFD analysis was some post-processing of the results, either morphological post-processing, so meaning, for example, we computed the tortuosity of the center line, the distance to the center line for every point, etc. And so we had global measures like the tortuosity of the aneurysm, or local measures that we computed on these different zones, on the different patches. So regarding morphological quantities, for example, we computed the ILT, so the height at every point of the thrombus, how much thrombus coverage there was, the distance to the center line of each of these points. And for hemodynamics, we post-process the hemodynamics CFD results to get different metrics. So wall shear stress, oscillatory shear index, or ECAP, or resistance times. I mean, these are typical measurements to quantify if particles will stay close to the wall or not, that have been reported to be related to platelet adhesion and thrombus formation. So in a first step, what we did is we considered all these patients with all these different scans and analyses, and the control cases as well. And we did some testing to know, just purely statistical tested to know if there were some metrics that were associated to being in either the control group, so where there is no risk, or low risk or high risk. So we divided the patients being high risk if their maximum diameter was more than a certain threshold. So this was like a clinical available data, or if the maximum diameter had a certain growth, and that this growth was higher than a certain threshold. If not, the patient was considered as a low risk. And there is irreversibility from low to high risk. So actually, with this first analysis, we saw that there were indeed some metrics that could distinguish the three different groups. So we thought, okay, maybe then we can go further and we can see if there are correlation between some of these morphological metrics and some of these hemodynamics metrics. So that we can maybe understand the relationship between hemodynamics and growth. So thrombus growth, for example. So we tested these correlations. So for example, here, distance to the center line versus this ECAP, this hemodynamics quantity. And in some patients, you can see that we got very nice correlation. And in some patients or some scans, the correlation, like there was not really a good correlation. And actually, if we do that for like all the patients, so what we found is that, okay, we could find some degree of correlation. And so this was assessed by this Spearman's rho coefficient, which basically gives the goodness of correlation for a monotonic function. But when it's zero, meaning it means that there is no correlation. When it's positive or negative, it means that you do have some meaningful correlation. So what we found, which was also found in the literature, is that, for example, the distance to the center line correlated negatively with wall shear stress information, and positively with measures of resonance time particles. But as you can see, there is really a wide spread of this rho coefficient. So really, it's not possible to find like a single nice correlation that could explain, that would be like the overall law of growth relating distance to the center lines, so the growth, and some hemodynamics feature. And especially for the thrombus thickness, you can see the widespread of these rho coefficients. So here I want to point out an important thing is that in some papers where they had access to maybe 6 or 10 patient cases, they had found some correlation, but maybe they were in this range, or maybe they were in this range, and then that's why they could find some correlation. So here I insist on the danger of looking at what's happening on small cohorts. I mean, it can generate hypotheses, but then these hypotheses really need to be tested on larger cohorts. This one of the main take-home message of this work, actually. So then what we did is to nevertheless, because we saw that there was nevertheless some, I mean, the first analysis had revealed that some metrics could classify patients into low and high risk. So we thought, okay, let's try to use a classifier, so a machine learning approach, to see if from data taken at time n, we could predict the risk at a later time. Okay, so we had this definition of high risk versus low risk. And what we did is to use machine learning. So we use all these label data. Okay, so for example, all the hemodynamics information of a scan, and we knew this if this scan at time t was of low risk or high risk. Okay, we cleaned up we selected some features with principal component analysis, and then we use machine learning to train the model to predict the change of risk at a later time, because we had access to this information for the other scans. And here's what we found. So if we use only the maximum diameter, the current clinical criteria, we found in a ROC curve, which is a curve that relates sensitivity to specificity, and luck is represented by the diagonal. We found that the area under the curve, so the area under this blue curve, which is what matters to have a good test, was 0.75. In fact, the best test that you can imagine is to have something that goes directly that is very, very sensitive immediately. And when you change the threshold of your diameter, it stays very sensitive and very specific. So you would have an area under the curve of 1 in the best scenario. So 0.75 is not too bad, and it was also reported in the literature. But the question was, can we do better? So if we use only clinical metrics, in fact, you do or morphometric metrics alone, or hemodynamics metrics, what do you arrive at? So using clinical features only, in fact, you do a little worse than the maximum diameter. And if you use morphometric features, in fact, you increase a lot your predictor capability. Hemodynamics alone even more. And if you combine everything, then you get the best predictor. So what's really interesting here is that, in fact, already only a morphological analysis gives you a very good predictor capability about low risk versus high risk over time. So this was an example here where CFD can be used in conjunction with machine learning to predict some growth phenomena, which is important in a clinical practice. Of course, it needs to be validated with a larger cohort. And now in the remaining time, I would like to use the opportunity to show some more recent work on simulation to better understand and predict surgeries in the context of liver disease. So here, the context is liver surgery. So liver has about 25% of the cardiac output. It can regenerate over time. It has a lot of very important function in the body, and it has a dual perfusion, meaning it's perfused by arterial blood and venous blood that it has to take care of. And then blood goes through the small units to be detoxified, etc. And then blood drains back into the hepatic vein and back to the heart. So in a number of diseases, liver transplantation of, for example, a small liver or partial liver resection leads to a small liver remaining after the surgery. And what the clinicians wanted to understand is really the relationship between liver volume, liver hemodynamics, and liver function to avoid liver failure after the surgery. So what we did in the first step to understand this phenomena is we did some, my colleagues performed some surgeries on pigs where they removed 75% of the liver. And we took some pressure and flow measurements during the surgery. So hepatectomy is when the part of the liver is removed. So we had access to pressure and flow measurements at different parts of the circulation and inputs and outputs of the liver, so that we could understand the important pressure and flow changes due to the surgery and maybe control these changes, for example, by an annulus to improve the regeneration of this organ afterwards. And first, we wanted to understand the relationship between the surgery and the liver hemodynamics. So we used this 0D type of model with a detailed model for the liver. We could also put what's happening during the surgery, like blood loss. And so here is what we achieved. So first, we tune our model to reproduce the experimental measurements. So the dashed are our results, and the plain are the experimental measurements for some pressure and flow. So the two flows going inside the liver. So then in the next step, we try to predict the outcome of the surgery in terms of flow changes and pressure changes. And what you see that we could capture some of the flow changes pretty well, also the increase of pressure at the entrance of the liver or across the liver. But for some other measurement, it was not so satisfactory. And in fact, we understood that we had to take into account what's happening during the surgery, so blood loss, infusion, etc. So overall, the model permitted us to understand why there is this huge decrease in the arterial flow rates entering the liver. It's purely mechanical. There is no need for an adaptation process, which was all over the place in the literature. Second, we understood that the decrease in the portal flow and in the arterial pressure was mainly due to blood loss, and this should be back to normal with the blood volume back to normal. So in fact, the right simulation could be what's happening when the pig is back to a normal state. And more importantly, we understood why the liver pressure gradients, in fact, the pressure difference across the liver is only increasing by a factor of 2 and not a factor of 4, as we would have thought with some kind of simple resistance change model, because there are at least 3 phenomena playing in and that we could understand in the model. So this was the first work on pig, and then we thought, okay, can we?
We should finish in around 5 minutes if it's okay for you. Yeah.
Okay, sounds good. So we thought, okay, we understood some things on the pig. Can we also use this kind of modeling approach to understand what's going on in patients? So in patient, the context is that so at least a few years ago, when we began to work on this topic, the patient selection for this partial hepatectomy, so removal of the liver, was that if there was hypertension in the portal pressure, so the venous pressure going in the liver, the recommendation was that these patients should not have partial hepatectomy. But then a few years ago, the recommendation changed regarding that topic, and several risks were identified based on if you needed to do a minor, so a small partial removal of the liver, or a major one. But the problem is that should we consider portal hypertension before the hepatectomy or due to the hepatectomy? Because in fact, there can be a pre-existing one, but the surgery is also introducing potentially further hypertension. And really, there is no tool currently to predict that aspect. So this is where we used our modeling approach with two parts of the liver, the right side and the left side. We use patient data to parameterize the model. So for the volume of the liver, what was going to be removed, and different quantities that we could measure at the beginning of the surgery. So for now, we use quantities measured at the beginning of the surgery. We tune our parameters, and then we simulate the surgery. We can also take into account changes of blood volume or heart rates or vasoconstriction, vasodilation phenomena occurring during the surgery. So what we found when we compared at the end of the surgery what the model predicts here, for example, for the portal pressure versus the measurement, is that we could predict reasonably well this pressure, and also the same for the gradient, both with like standard simulation or what I call adjusted simulation, so adjusted to the perioperative event. And in fact, when we look at the correlation of this computed versus measured pressure, so here for the adjusted simulation, it's pretty good. More importantly, we could have a good prediction of the cases that are considered hypertensive based on the clinical recommendation. Another way to look at the results is to do a Bland-Almond graph. So on the x-axis, you do the average between your measurement and your prediction. And on the y-axis, you do the difference between the two. So what you're aiming at is that all the points stay quite close to zero, the difference being small. So our goal was that the difference would stay within 3 millimeters. And what you can see here is that indeed, this was the case for most of the patients. And most importantly, for the 4 patients who unfortunately underwent a postoperative death, the prediction of the pressure was pretty good. And also, if we consider the current preoperative cutoff measure of the gradient of 10 millimeter mercury, we could predict it. I mean, we could, predict things pretty well with the adjusted simulation. I think there is still some work to be done to better understand what's going on during the surgery to really use this kind of approach. Okay, I'm going to skip the last example of how we looked into a novel idea of surgery with this kind of model and conclude. So I hope I convinced you that modeling and numerical methods have matured for patient-specific simulation, that such simulations can be used to understand a system, a disease, a treatment, or to predict, plan an intervention for a specific patient, or to test new treatment ideas of clinicians. Do we need to intervene if there is valve regurgitation before or during another surgery? Also, machine learning, in my opinion, can be complementary to biophysical modeling, especially because sometimes we don't have equations really to model the growth. And so machine learning can be a palliation to that. And overall, there is great tool progress, but validation with access to large cohorts really remains an issue, I would say, in the field. We really need more impact on patients, and that's why, I hope that this ERC will help us to do that. So, we really need a lot of students engaged in this topic to really do more impact on patients. So I invite you to get involved. Thank you, and I'm happy to take any questions.
Thank you, Irene. Really wonderful talk. I mean, really in a lot of different applications. That's brilliant. So the chat and I mean the Zoom is open for questions from the audience. If anyone wants to just think about potential questions, I could start. I have trillions of things to discuss and questions. I mean, one is really related to one of the last points, validation and benchmarks and what should we do as a community to improve this? Because at some point, even you were saying, well, I mean, you find results all over the place in the literature. You have a review, you do a review of a particular type of models, and you find all the variety of boundary conditions, pressure in the outlets, velocity in the outlets, the other way around. I mean, and you don't know. If you want to start in a given problem, it's very difficult to really have a feeling on which are the best boundary conditions. And my question is, how can we improve this? Beyond, okay, having access to a large cohorts, it's okay, but do you think this is really the key point for having more group-wise work towards this?
So I would say, I mean, first of all, if you want to be able to predict the effect of something, so for example, if you intervene locally, you put a stent, or you you change your tube configuration because there is a surgery or something like this. So if you want your simulation to be predictive, then you need to have at least some of the boundary conditions that are where you don't prescribe flow or pressure, because otherwise you're prescribing these quantities to be fixed, so they cannot change in the simulation. So that's why it's important to have at the outlet, especially like some, for example, at least some resistance boundary conditions, so that you have a relationship between pressure and flow, but you're not imposing how much flow goes out of that outlet, or what's the pressure there. And then depending on the question you're trying to address, you will have to and the question you are trying to address, and the knowledge also about that question, you can make some hypotheses about boundary condition, and then they need to be tested by other measurements. So, for example, in the liver, when we started to look at this liver surgery, like the surgeons had told us, oh, you can consider like the portal flow to be completely constant during the surgery, and the arterial pressure to be completely constant during the surgery. And so first we had just started with the liver model, not taking into account the rest of the circulation. And we could not reproduce this change of arterial flow, like removing 75% of the liver. You're making a major resistance change, in fact, to the liver, like you're increasing by factor 4, basically. And so, okay, we could reproduce some of the features, but we could not completely reproduce what was going on for every pig. And we understood that, in fact, well, what the surgeons were telling us was maybe okay on average, but it was not always the case. And also due to the hepatectomy, in fact, the portal flow decreases a little bit because there is an increase of the resistance, and so the input boundary conditions are not completely fixed.
So the message is, don't think that whatever clinicians say is ground truth.
Also, yeah, that's another point.
Everything data is not ground truth, total ground truth, and whatever clinicians say is not totally ground truth. You really need to think that sometimes there is uncertainty on these things, right?
Yes, so yes, it's true. So maybe another message that is important for me is this tight collaboration with experimentalists or clinicians. So in this field, like, it's not like you try to understand, you get the basic of what's going on, and then you go by yourself, you do your little work, and then you have the results. It's really requiring, but I think it's true in other fields of bioengineering too, like a tight collaboration with clinicians and experimentalists, and going back and forth, going to the OR to understand what's going on, to see the variations in the measurements, to have the clinicians involved in
Mm-hmm.
understanding the model. In
Exactly.
yeah,
Exactly.
I think
We
it's
have
key.
a couple of questions
Yeah, sure.
from the audience. Marion Tacone says, I would like to know how you deal with the errors induced by the clinical measurements, well, it's related to what we were discussing, or the when, how, where the measurements are done to validate your models. So basically, yeah, how do you take into account uncertainty in the measurements, in the process of validation, of data assimilation?
Yeah, that's a great question. So here too, it depends on the cases. So in fact, for example, for the aneurysm work, like we didn't have access to the flow, the inflow waveform. I mean, to the flow rate of the patient. So here there was a huge uncertainty. The student prior to work with me had validated, for example, that the flow he was getting inside the aneurysm was correct by comparison with MR measurement at this location for a few patients. So that's a way to validate. But I agree that what's needed is really to do some uncertainty quantification, and we've done a little bit of that on the congenital heart disease part, but for the liver, this is actually the next step. And actually I have a postdoc working on that topic right now, because indeed there are uncertainties in these clinical measurements. And so the output that we give need to not only be a number, but with a certain uncertainty associated to that, for sure.
And Robin May is asking about the valve regurgitation modeling, that he showed some changes in the PV loops of the ventricle, that how this kind of simulated PV loops could be validated if you had some kind of, I don't know, pressure or invasive measurements to validate these PV loops.
So in the two patients I showed, in fact, I showed that, so we did not validate the PV loop per se, but we had access to the pressure over time in the single ventricle that we didn't use for training of the model. So this pressure over the cardiac cycle were a good validation. So now we didn't have access for these cases to the volume over time. This can be acquired clinically, but it's not that easy to get. Either you can have it by a special catheter, and that also can measure a surrogate of the volume of the chamber at the same time. And so you can have access to the PV loop, or from echo or MRI, but it's really not trivial to have access to PV loop. It does exist, but it's we didn't have access to that there, just the pressure.
Jerome, I guess I need you to give permission. Well, you can ask a question. You are the organizer, so I cannot tell you no.
No, that's fine. I mean, we're good in time because actually, maybe Anita can stop the recording, and so we're entering in the break. So in general, we're asking them, the speakers, to stay in the break for more informal discussion.
Yeah, sure.